Okay, this is now another paper, May, June 2021, paper 4.2, and move to question number 1. The question is, define gravitational field strength. So the answer is, it is the gravitational force experienced per unit mass in the gravitational field. So this is the answer for this definition. Okay, next, isolated planet of the uniform sphere radius is given, mass of the planet is given, and the period is given. The question is, for that object resting on the surface of the planet at the equator, calculate the three significant figure, the gravitational field strength. So at the surface, gravitational field strength means small g formula is capital G, capital M over radius square. So 6.67, 10 power minus 11. This is the capital G, universal gravitational constant, and the mass is given 6.42 into 10 power 23. Divided by the radius is given 3.39 into 10 power 6 per square. And after the calculation, the answer is coming 3.73. Now the next is centripetal force, centripetal acceleration, sorry. The acceleration is equal to r omega square, is equal to r omega, r is the radius, and the radius is given 3.39 into 10 power 6, and omega is 2 pi over time period square, so it will be 3.39, 10 power 6 to 3.14 divided by period is given in hours, 24.6, so 24.6 times 3600 and whole square. We have to convert this period into second. So after calculation, this answer is coming 0.0171. Now the force per unit mass exerted on the object by the surface of the planet. So according to this formula, force of gravitation is equal to centripetal force plus weight of the object. So the force of gravitation minus centripetal force is equal to the weight. This is actually the force experienced by the object by the surface of the planet. Now, it can be written as mg, the force of gravitation, mean mg at the pole, because the force of gravitation exactly equal to the weight at the pole minus centripetal acceleration. This one is m r omega square at the equator, and this is mg. So actually g is required here, so m cancelled. So g at the surface is 3.37 minus the centripetal acceleration is 0.0171. So this is the force per unit mass, and its answer is 3.71. So explanation of this, actually weight is the difference of the force of gravitation minus the centripetal force at the equator. So we have calculated g at the planet, mean g at the surface, minus m into centripetal acceleration, and this is equal to mg, so m's are cancelled. So this is actually g, which is gravitational field strength, mean the force per unit mass on the object due to the planet. And the next, the question is, an ideal gas has a volume, its pressure, its temperature. Now the volume 3.1 to 6.3, because the gas suddenly expands, this is the pressure and the new temperature Tf. The question is, show that the number of the gas molecule is 6.6, 10 power 23. So we will use this. So first, PV is equal to nRT. or we can write PV is equal to NKT. So here the number of the particles is equal to PV divided by KT. So the pressure is 8.5 into 10 power 5 and the volume is 3.1 into 10 power minus 3 divided by K, the Boltzmann constant, 1.38 into 10 power minus 23. Temperature in Kelvin, initial is given, it's 290. And after the calculation, we will get the answer, 6.6 into 10 power 23. So it's proved. Show that the final temperature of the gas is 190. Look, PV is equal to nRT. This is constant. So PV over T is constant. So we can write P1 V1 over T1 is equal to P2 V2 over T2. Now, this P1 is 8.5 into 10 power 5, V1 3.1 into 10 power minus 3, temperature is 290, and when gas expands, its pressure is 2.7 into 10 power 5 times the new volume 6.3 into 10 power minus 3 and the new temperature required. So after the calculation, you will get the same answer, 190 Kelvin. Now the next, the average translational kinetic energy of the molecule of an ideal gas is given by the expression where T is the thermodynamic temperature, K is the Boltzmann. Calculate the energy of this ideal gas. Look, the change in the energy for the ideal gas is equal to change in kinetic energy. This is the kinetic energy of the one molecule. So the total kinetic energy will be 3 by 2 NK. And due to change, we will use the change of temperature. So 3 by 2, the number is calculated 6.6 into 10 power 23. K Boltzmann constant 1.38 into 10 power 23. And the change of temperature is 290 minus 190. Temperature is decreasing. So the answer is coming after the calculation, 1400. And this is the decrease in the internal energy because the temperature is decreasing. Next, use the first law of thermodynamics to explain why the external work W on the gas during the expansion is equal to increase. Look, according to first law, plus Q is equal to plus W minus work. So it becomes U is equal to Q plus W, but here it is mentioned that during expansion, no thermal energy is transferred. It means the Q is 0. So when Q 0, U is equal to W. Hence, the work done on the gas is equal to increase in internal energy. So this is proof. So work done on the gas, expansion is equal to increase in internal energy. So we have to write the statement here from this relation. And the next, the question is, a U-shaped tube contains some liquid column in each half of the tube is L. So the liquid column are displaced vertically, the liquid then oscillate in the tube, the liquid level are displaced from the equilibrium position and it's executing simple harmonic motion here. So where G is the acceleration, explain how the expression shows that the liquid of the tube is undergoing simple. Look, G is constant. So the total length of the column of the liquid is constant. So we can write A is equal to minus constant times X. It means A directly proportional to minus X, which is showing that acceleration is directly proportional to displacement, but opposite in direction due to the negative sign. This apart. Next, Length is given 18 and the period is required. So look, omega is equal to 2 pi over t. But here, the omega square, because the acceleration is equal to minus x omega square. So we will use the omega equal to g over L. So omega square is equal to g over L, and omega is 2 pi over t square g over L. So it can be written as t is equal to 2 pi under root L over G. This expression can be written like this. So this is 2 times 3.14 under root. The length is 0.18 in meter, G value 9.81. And after the calculation, let me calculate this is 0.85. Next, the oscillation of the liquid in the tube are damped. In any one complete cycle, the amplitude decreases by 6% of its value. So this is the decrease for one oscillation, for one cycle. Energy of the oscillation after 3 cycles. So look, initial amplitude is A0. After 1 cycle, it will be 94% because 6% is lost. So 94% of A0. And after second oscillation, it will be 0.94 times the previous 0.94 A0, and for the third it becomes 0.94 A0, and this value is approximately 0.94 cube. So it is 0.83 A0. So energy is directly proportional to amplitude square. After 3 oscillation, the amplitude is 0.83 I0 divided by initial is A0, but due to square, we have to take the square. So it is cancelled. So answer 0.83 square. So the 0.83 square answer will be 0.6898. So 0.69. This is the ratio, no unit. And the next question number 4 is, a sinusoidal carrier wave has a constant amplitude and frequency 1.2 megahertz. The carrier wave is modulated by the signal wave that a 1 volt displacement of the signal wave causes a change of the frequency 25. A signal wave has a frequency 8 kilohertz, amplitude 2. State the name of this type. Constant amplitude, I mean this is the frequency modulation. And for this period, they determine the variation, if any, in the amplitude. No variation, no change. Because it is written amplitude constant. No change. Mean the 0. And its frequency. So frequency modulation. So frequency is changing plus minus 50 kilohertz. And the rate of change of the frequency is equal to the frequency of the signal. So at the rate of 8,000 hertz, mean 8,000 times in 1 second, the frequency is changing plus minus 50 kilohertz. And the next, an audio signal transmitted by means of the modulated radio wave, the variation of the frequency of the amplitude of this. So here is the amplitude modulation. For this transmission, determine the wavelength in kilometers of the carrier wave. Look, V is equal to F lambda. So the lambda is equal to V divided by F. Radio wave is traveling with the speed of light in 10 power 8, and the frequency is this. This is the frequency of the carrier wave. which is 240 into 10 power 3 due to the kilo, and after the calculation, the wavelength is 1250 meter, but in kilometer, it will be 1.25. The bandwidth, this is the bandwidth, this one, this gap. So 225 to 255, this is 30 kilohertz. And the frequency of the audio signal, look, the frequency of the audio signal so the bandwidth is equal to 2 times FA. So FA is the half of this bandwidth. So it is 15 kilohertz. Next, an isolated metal sphere of the radius r is charged so that the electric potential at the surface is V naught. Sketch the variation with the distance x from the center of the sphere of the electric potential. Your graph should be from x0. So look, from one end to the other end, the electric potential remains same, constant. So from the center to the surface, it is constant. V is equal to 1 over 4 pi epsilon naught Q divided by D. So V and T inversely proportional. When this distance becomes 2r, it becomes half. So here the 0.5. When it becomes 3r, it will be 1 by 3, mean 0.33. So approximately it is here. So this is the curve. And the next, the photon having the wavelength of lambda are incident at the metal surface. The maximum wavelength for which there is a emission of the electron is lambda naught. So at the lambda naught, this is the threshold wavelength, no kinetic energy possessed by the photon. Mean at this lambda naught, the kinetic energy is 0. And the next, for the photon of the wavelength lambda by 2, the maximum kinetic energy emitted is Emax. So at lambda by 2, the kinetic energy is Emax. And then sketch the variation of the wavelength lambda of the maximum kinetic energy for the value of lambda by 3 and lambda by 2. Okay, so look, energy is equal to hc over lambda naught. And equation is kinetic energy is equal to hf minus work function. When there is no kinetic energy, then this hf, hc over lambda naught is equal to 5. I mean, this is the threshold wavelength, and this is the work function. Now the question is the energy E is equal to hc over lambda minus phi. So the energy is required when hc over lambda is lambda naught by 3. So 3 times lambda naught, and minus phi is hc over lambda naught. So it becomes 2 times hc over lambda naught. Now hc over lambda naught is energy. So it is 2E. So at lambda by T, the energy is twice this one. So the graph is like this, negative gradient, and it's a curve, and it's stretching the x-axis here. So this is a graph. Next, C part, a pure sample of the radioactive isotope and not nuclei, the half of the isotope T half, the product of the radioactive decay is stable. The variation with time T of the number N of the nuclei radioactive isotope is shown. Labeled on the time axis, the time half-life and time second half-life. Okay. So after 1 half-life, the number becomes half. So this is the first half-life. And then it becomes 1 by 4. So this is the second half-life. This point and this point. And the next, sketch the variation with time T of the number of the nuclei of the decay product for the time 0 to time T. sketch a variation of the number of the nuclei of the decay product after time. So look, initially, when the radioactive is N0, start of the decay, the daughter element is 0, and after half-life, it becomes half, and after the second half-life, so it becomes this number, because this is decreasing, the new daughter is decreasing, and after the full time, it is 1, 2, 3, 4. So 1, 2, 3, 4, this is the point. So this is the graph for the daughter nuclei after the decay of the first. And the next, the two flat metal plates are held a small distance apart by means of the insulating pad, as shown in the figure. Explain how the plates could act as a capacitor. Look, when voltage is provided, voltage or the potential difference is provided, work is done on the charges of plates which increases their spacing, and work is stored as electric energy. So this answer. So work is done, separation increases, and the work is stored as energy, so it behaves like a capacitor. And the arrangement in the figure 6.1 had capacitance C. When the two-way switch is moved to position A, look at this A position. This is a charging, the capacitor charged so that the potential difference across is V. When the switch moves to B, the capacitor fully discharges through a sensitive ammeter. The switch moves repeatedly from A and B so that the capacitor charges and then discharges with the frequency F. Show that the average current of the ammeter is this. Look, I is equal to Q divided by T. And the Q is equal to, in the capacitor, is CV divided by T. And T is actually the period here of charging and discharging. So 1 divided by period is equal to frequency. So I is equal to CV times 1 over T. So it is CV and F, hence proved. For a potential difference V of the 180 and the frequency of the switching 50 Hertz, the average current I in the ammeter is 2.5 microampere. Calculate the capacitance as picofarad. So same formula, I is equal to CVF. The capacitance is required. So C is equal to I divided by VF. I is given 2.5 into 10 power minus 6 divided by voltage is 180 and the frequency is 50. After the calculation, the capacitance is 280 into 10 power minus 12. Actually, it's coming 2.8 10 power minus 10. So for the pico, it's converted. So it is 280. So 2.8 10 power minus 10, but we have to convert this in pico. Next, a second capacitor is connected into the circuit and the two capacitors in parallel. Yes, in parallel, capacitance increases. State and explain the change, if any, the average current in the ammeter. So look, in parallel, combination of the capacitor, capacitance C increases. So more charges are stored at the surface of plates, thus current increases because Q is IT and charge directly proportional to I. Next, question number 7 is, two properties of the ideal op-amp are infinite input impedance and the infinite bandwidth. State what is meant by infinite input impedance. So impedance, infinite input impedance. mean the resistance, no current, enters or leaves through the input terminal to op-amp. Next, infinite bandwidths, the gain of the operational amplifier is equal for all frequencies of input voltage. In all frequencies of the input voltage are accepted by it to give this output. Next, this is the circuit. A student using a negative temperature coefficient thermistor. This is the thermistor. In the circuit, these two resistors are connected in potential divider. This is the input resistor, and this is actually the supply voltage. Show that the potential at the X is this. So potential divider formula, Px is equal to Rx divided by Rx plus Ry into EMF. So it is 400 Rx divided by 400 plus 1100. Look, so this is actually the input voltage here. So this is the Rx because the voltage here required. So, and this is Ry, and the EMF is 1.5. So after the calculation, 400 divided by 1500 times 1.5, the answer is coming 0.40 volt. Next, the thermistor has a gain of 360 kilo ohm at a particular temperature. For this temperature thermistor, calculate the magnitude of the reading. I mean, output is required. Look, output over input. This ratio is called the gain. And here it is equal to minus Rf over Ri. So output, the Rf is the combination of these two resistors. So sum of these two resistors, 360 plus 100 divided by the Ri is 96 and multiply by input. Input is 0.4. So after the calculation, so 460 divided by 96 multiply 9.4, it is coming 1.9. The temperature of the thermistor increases. State and explain the effect on the change of the magnitude of the reading, mean output. Look, with the increase of the temperature, resistance of thermistor increases with temperature. When resistance increases, mean RF resistance increases, output increases, gain increases. Thus, V out, output increases because the gain increases. And the formula is gain is equal to minus RF over Ri. So RF increases, gain increases, mean output increases. Next is explain why the amplifier circuit will no longer indicate temperature changes when the magnitude of the gain of the circuit is greater than 12.5. So for gain 12.5, the output is maximum 5.0, which is equal to the supply voltage. So beyond this gain, if the gain is greater than 12.5, then the op-amp is saturated. No output, because after the saturation, there will be no output. So no, it indicates no change of temperature, so no output. So when output becomes equal to the supply voltage, it becomes saturated. And after this gain, no output from the op-amp. Next, define magnetic flux density. So we have to define formula P is BIL sine theta, mean B is equal to F over IL sine theta. So magnetic flux density is the magnetic force experienced per unit length conductor, per unit ampere, or carrying per unit ampere current and placed perpendicularly inside the magnetic field. I repeat, magnetic flux density is the magnetic force experienced per unit length conductor, per unit current, and placed perpendicularly inside the magnetic field. Next. Electron, each of them has m and q, are accelerated from rest in a vacuum through a potential difference v. Derive the expression in terms of m, q, v for the final speed. Look, work is equal to change of kinetic energy. The electric work is charge multiplied by voltage potential difference. It's equal to half mv square. So 2qv over m is equal to v square. Hence, speed is equal to 2qv over m under root. This is the expression. Accelerated electron in the B are injected at the point S into the region of the uniform magnetic field of the flux density B, as illustrated. And the electrons move at the right angle to the direction of the magnetic field. The path of the electron in the circular of radius r. Show that the specific charge q by m of the electron is given by the expression q by m is this. Look. Electric force is equal to magnetic force. Sorry, centripetal force, not the electric field here, the centripetal, because the circular path. So, sorry, centripetal force is equal to magnetic force. And the centripetal force is equal to mv square over r. And this is bqv sine theta, but perpendicularly entering perpendicularly, sine 90 is 1. So this v square cancel with v. So from this we can write v is equal to bqr over m. But here in the previous part, v square is this 2qv over m. So v square is equal to 2qv over m. So this v is replaced with this v. It becomes b square, q square, r square over m square is equal to 2qv over m. Now, one q cancelled, one m cancelled, one left, one m left, one. So q divided by m is equal to then this 2, this v divided by this b square, this r square. So b square, r square, hence proved. Now electrons are accelerated through a potential difference of 230. Electrons are injected normally into the magnetic flux density 0.38 millitesla, and the radius is 14. Use the information, calculate the specific charge. So the previous formula, q divided by m, 2v, b square, r square. So 2 times voltage 230, and the b is 0.38 milli mean 10 power minus 3, it's square, and the radius in meter 0.14 square. Now calculations, let me calculate. So 0.23, 2 into 230, 0.38. Yes, the answer is coming 1.6 into 10 power 11. This is the specific charge. Suggest why the arrangement in second using the same value of the b and v, look, this is same, is not practical for the determination of specific charge of alpha. Look here. Electrons, specific charge, q by m, and the alpha, this is for the electron. For the alpha, the charge is double, and the mass is 4 times u. It means the q over m of the alpha is greater than the q over alpha for the electron. Thus, according to this formula, when this is large, the path is not same. path will be not same. So this is the reason suggests why the arrangement outlined using the same value of the B and B is not practical for this information. So we cannot get this 14 centimeter path because the charge of the alpha is double than electron and the mass is too large because the electron is similar to the beta. And look, electron is similar to beta, its mass is 9.11 10 power minus 31, but this mass is 4 times U, is too heavy. So the answer, sorry, this alpha is 2Q, so 2, 1 divided by 2. So here we have to change the sign. Look, this charge to mass ratio. We have to calculate. So the different, instead of greater or smaller, we can write here the charge to mass ratio of the alpha is different due to different charge and different mass than the electron. That's the path would not be the similar, not be the same, because here no calculation. So we have to just mention that both Q2 charge to mass ratios are not similar. So the path is not similar. There is no need to mention greater or smaller because the calculation is required. Move to the next, state 2 situation in which the charged particle in a magnetic field does not experience a force. So simple, the charged particle stationary. When the charged particle is at rest, it experiences no force because F is equal to BQV. So when V0, force 0. And the next, state 2 situation. So other situation is charged particle is moving parallel to magnetic field lines or magnetic field, because the formula is BQV sine theta. So when theta is 0 for the parallel, the force becomes 0. And the next, a loosely coiled metal spring is suspended from the fixed point as shown in the figure. Electrical connections are made to the ends of the spring by means of the flexible lead. The length of the spring is measured before switch is closed, and then again after the switch is closed. When the switch is closed, the magnetic field is set up around each coil of the spring. By reference to these magnetic field, explain why there is a change in the length of the spring. State whether the spring extends or contracts. Look. When current is supplied, there is a magnetic field around each loop of coil. In all loops, magnetic field is perpendicular to the direction. Magnetic field is perpendicular to the direction of the current because field is circular. Now, due to same direction current in each loop, there will be attraction which can be determined by Fleming left-hand rule. So there will be contraction. Because we have done two wires parallel carrying current in the same direction attract each other. So we have to apply the same rule here. So according to the situation, you can change your statement. Now the next is with the switch is B closed, a small mass of the free end of the spring is now made to oscillate vertically. So use the principle of electromagnetic induction. Why the small fluctuation in the current in the spring? Okay, when it oscillates, oscillation causes varying magnetic flux, which is cut by the coil loop according to Faraday's law, and EMF is induced, which causes the current in the coil. Now the next is, by reference to the heating effect, explain what is meant by the root mean square value of an alternating current. So this root mean square value of the alternating current is equal to that direct current which produces same heating effect as produced by alternating current. Okay, the next part is the variation with time t of the two current I1, I2 is shown. So one is a sinusoidal wave, other is a square wave. And the question is for the 10.1, which is sine wave, the peak value. So from the graph, we can read the peak value. It is approximately 2.6. And then we have to calculate the RMS value. So IRMS is equal to peak current divided by under root 2. So after the calculation, so 2.6 divided by under root 2, it's coming 1.8. And the second is the square wave. So RMS value and the peak value both are the same. So the RMS value and the peak value 2. So both are 2. And the next is V is equal to this. The variation with time t of the supply voltage to a house is given by the expression V is equal to 240 sine kt. So it's similar to V is equal to V naught sine omega t, where V is the volt, t is the second, k is the constant with units radians per second, mean this is omega. The frequency of the supply is this, determine the value of k to two significant figures. So k is equal to omega. By comparing these two equations, V is equal to omega. So omega is equal to 2 by f. So k is this. So 2 multiplied by 22 by 7 multiplied by frequency is 50. After the calculation, it is coming 310. Next, the voltage supplied to a heater. The mean power is 3.2 kilowatt. Calculate the resistance. Look, power is equal to V square over R. And this V is RMS. So we can write power is equal to peak value divided by under root 2 square divided by resistance. So the resistance is equal to V naught square divided by 2 times power. So it is 240 square divided by 2 divided by 3200. So the answer calculation is 9.0. And the next is state the purpose of the computed tomography. So it produces three-dimensional image of the holes of the structure. It produces three-dimensional image of whole structure of the body. This is the purpose, 1 mark. Outline the principle of the CT scan. So in CT scan, we use X-rays. And this X-ray is used to get image in sections. X-rays are taken from different orientations, from different angles. And each image is two-dimensional of each section. This procedure is repeated for many sections. When all results, mean images, are combined, then final image gives detailed information. So you can write this whole paragraph according to these points, okay? Next, what is meant by the photon? It's a particle of light packet of energy and electromagnetic in nature. The next, a stationary nucleus of Samarium-157 emits a gamma rays photon of energy 0.57 MeV determined for the one gamma ray photon, its wavelength. The energy is equal to HF, which can be written as HC over lambda, because V is equal to F lambda, so C is equal to F lambda. So F can be replaced by C over lambda. So H Planck constant, 6.63, 10 power minus 34, speed of light 3 into 10 power 8, and wavelength is required, and the energy is 0.57, and mega electron volt mean 1.6 into 10 power minus 13. So calculation, so this answer for the lambda is 2.2 into 10 power minus 12. So 2.2 10 power minus 12. Its momentum. Momentum is equal to H over lambda. So 6.63 10 power minus 34 divided by wavelength. Calculated 2.2 10 power minus 12. So the momentum is coming 3.0 10 power minus 22. And the next part is use the answer to determine the speed of strontium nucleus after the emission of the photon. Look, we have momentum, but the momentum is mv. So v is equal to momentum divided by mass. So the momentum is 3 into 10 power minus, I think, 22, yes. And divided by mass of this 157. So the mass formula is A times U. So A is 157 and the U is 1.66, 10 power minus 27. Now calculate this. So 3 times 22 minus 1. And the answer is coming 1.2 into 10 power 3 meter per second. By reference to your answer in C1, explain qualitatively why the speed of the Samarium-157 nucleus may be assumed to be negligible compared to the speed of the photon. So photon is traveling with the speed of light, 3 into 10 power 8 meter per second. But this Samarium-157 is traveling with 1.2 into 10 power 3. So it's too small. So speed is much smaller. Thus, we can ignore it. Okay. So this is the whole paper. So revise it.